Hi, everybody. Welcome to this webinar organized by the Institute of Physics on two-dimensional materials, which is actually celebrating the 10th anniversary of the launch of 2D Material, which is a journal from IOP, which is currently led by the editor-in-chief Wen-Sai Ren from Shenyang National Labs for Material Science of the Chinese Academy of Science. So we are very happy, privileged to have with us today 4 panelists who are all international leaders in the fields of two-dimensional materials. My name is Stéphane Roche. I'm Nuclear Research Professor at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona. And it's my great pleasure to chair this webinar entitled The Future of Two-Dimensional Materials, Grand Challenge and Opportunities. So I will start by briefly introducing our 4 panelists, Konstantin Novoselov, Johan Redwing, Yuri Gogotsi, and Pia Matevi. Then each of them will take about 5 minutes to give a short presentation. And then I will have a follow-up questions after the presentation, and then we will have a longer session of Q&A. So you are all invited to write your question in the chat while we are having this conversation, and then we will try to take as many questions as possible. Okay, in case we have some left question, we will communicate, share them with the panelists that can maybe answer offline. Okay, so let's start. First of all, let me introduce Konstantin Novoselov. So as everybody knows, Konstantin has pioneered the fields of graphene and two-dimensional material, and as when he was at the University of Manchester, UK, and has been awarded the Physics Nobel Prize in 2010. Since October 2021, Konstantin is a professor at the National University of Singapore, and he's also the director of the Institute of Functional Intelligence Materials, where there is one particularly interesting fact is that the Institute is using artificial intelligence to design and synthesize new forms of smart and multifunctional materials for application in advanced electronics, energy, bio, and healthcare, or membranes and coating. So very happy to have you, Konstantin. So I see that we already have your slide online. So please, the floor is yours for 5 minutes.
So thanks a lot, Stefan. It's really a great pleasure to be here. Very briefly, so of course this journal, the material started with graphene 10 years ago, but it very quickly evolved into many other two-dimensional crystal, and that's really exciting to see that the family of this two-dimensional material grows day by day. I think I lost count. It's probably easy few hundred experimentally isolated crystals, few thousand been predicted. But what is even more exciting that such two-dimensional materials, they provide a platform to create van der Waals heterostructures, which is basically materials on demand. You create artificial three-dimensional materials which can fulfill certain properties and certain functionalities for particular applications. So of course that's quite a number of different devices and different structures have been created, from the tunneling transistors to light emitting diodes as well. And the excitement here is of course that it's really you have a lot of flexibility and a lot of freedom when designing those new materials. And what was what really came as a surprise probably a few years ago, that it's not only the sequence, not only how many layers of different materials do you stack together, but also the way how do you do it, just putting different angles between those crystals would affect the properties of those materials. So that's all exciting, and of course, and we will get every year we get more and more knobs how to control the properties of those materials. Again, recently it became very popular to control the individual impurities and defects in those materials, either for the purpose of catalysis or for such applications as single photon emitters, for example. The question is really, I think we're now getting from the into the more structural. We require more structural ways how to design the properties of our materials, either two-dimensional crystals or van der Waals heterostructures, and that's really calls for new ways how to predict and compute those properties. And I think one of the way is the introduction of the artificial intelligence. So we see the creation of new databases of 2D materials, of the individual defects in those two-dimensional crystals, and that really helps to create materials with the predetermined properties. So that's the problem is that it's very there is of course a huge gap between what we predict in our computation and what we can actually create in the experiments, because those 2D materials, they appear not only with the in different chemical compositions. There are many different phases which often change their properties dramatically, and that's why we need novel. We need some breakthroughs in creating those databases. It's not only the static properties of materials which are required to be captured, but also the kinetics of the growth, which hasn't been done yet, and it really requires quite a lot of efforts. But also our heterostructures become larger and larger and larger. So we need to increase the performance of our computational resources like GST. So that's another direction which many groups are pursuing at the moment, how to understand the properties of heterostructures which contain thousands or tens of thousands of different atoms. So lots of efforts being paid on this way, and I really hope that once we fully master the computational part of the prediction of the properties of those crystals, but also capture the kinetics of the growth, it would bring us to the next level of the designing of the new materials. Thank you.
Thank you very much, Kostya, for the presentation. Just a curiosity question about because in your center, as far as I understand, you are considering a wealth of different type of materials beyond two-dimensional materials. But I have a curiosity question about what about graphene, like clean graphene? Is there any use of graphene that you are still considering in your center, or graphene combined with others?
Oh, it's of course, ideally, of course, we would love to look forward and to play with new materials every week. But graphene, still, it looks like a very special material, and for some reason, it every now and then it comes as a champion for many different applications. So we do come back to this material, often to graphene, often in combination with the other materials, not only other 2D crystals, but polymers, polyelectrolytes, and we find it that it really provides new applications every day, and that's and so we do have maybe about 20-25% of our efforts still on the applications of graphene in many different areas, from drug delivery to energy.
Mm-hmm. Yeah, thank you, Kostya. Thank you so much. So please remain on board for the discussion part. Our next panelist is Professor Joan Redwing. So she's a distinguished professor of material science and engineering and director of the NSF 2D Crystal Consortium and Material Innovation Platform of Penn State in the US. She's an expert in the field of MOCVD, processing of semiconductor thin films and nanomaterials, and she has a focused activity on the synthesis of transition metal dichalcogenides and the study of their optoelectronic property. The objective of her research is really to try to understand the fundamental mechanism of van der Waals epitaxy of these TMDs, and also to develop methods for wafer scale epitaxial growth and related technology. Joanne, floor is yours.
Okay, thank you, everyone. Hopefully you can see my screen fine, my slides.
Yeah, we do.
Okay, great. All right, first of all, I want to welcome everyone who is joining us for this webinar. I want to focus my comments on 2D layered chalcogenides. So this is a class of materials that have a very wide range of unique properties. And their ultra thin nature makes them of interest for a variety of device applications. So for example, some of the areas where there's current interest is in 3D integrated circuits. Let me just, so for example, being able to integrate logic devices with memory and with sensing. And 2D materials really have some advantages here in terms of their ultra thin nature and their flexibility and ability to stack layers on top of one another. Also, there are other applications such as in wearable electronics, flexible biosensors, and then of course devices that can be integrated into neural networks. So in addition to the semiconducting 2D materials, like the transition metal dichalcogenides, there are also topological insulators and superconductors that are of interest for quantum technologies. But all of these device applications need advances in the synthesis of 2D materials, specifically being able to do the synthesis at the wafer scale in order to advance technologies. So are you still seeing my slides? Okay, good, okay. All right, so let me just, okay. So over the last 5 years, there have been significant advances in wafer scale synthesis, specifically of transition metal dichalcogenides. Now there are two general approaches that are used. The first is to do direct deposition of the TMDs on amorphous substrates. So for example, oxidized silicon. The advantages here are that you can deposit the layers at low temperatures. So temperatures that are compatible with back end of line integration with silicon. Also, it's possible to pattern the oxide surface so that you can control the nucleation site, but there are some downsides. This process often requires the addition of growth promoters like sodium chloride, which can add impurities into the material. And also the lower temperatures can result in small grain sizes and high angle grain boundaries in films that are coalesced. But nevertheless, there have been some really impressive demonstrations. So for example, deposition of moly disulfide on 8-inch diameter oxidized silicon. The other approach then is to do epitaxial growth on single crystal substrates. So this would be a substrate like sapphire. The advantage here is that you can use the sapphire lattice to align the TMD domains so that you can reduce the number of high angle grain boundaries and get really large single crystal areas up to wafer scale. Also, you don't have to add growth promoters in this process in general, but there are downsides. It requires high temperatures for epitaxy. And it also, and this is probably the biggest downside, it requires the use of layer transfer to remove the film growth substrate to transfer it onto a silicon substrate for device integration. But again, there have been some really impressive demonstrations even over the last year. This is an example of a group from China that deposited moly disulfide again on 8-inch sapphire. Now, moving forward, there are a number of needs and also opportunities in this area. So as I mentioned, there have been very impressive demonstrations at the single wafer level. However, we need to move towards multi-wafer reactors that can increase throughput for manufacturing. So, okay, so as shown here, there are a couple different configurations that can be used for multi-wafer systems. Also, along similar lines, we need methods for in situ monitoring so that we can improve process control, and also reactor modeling to be able to model the thermal fluid environment of the reactors. This is necessary to improve uniformity and also just to get a better understanding of the fundamental mechanisms behind the growth of these materials. And then in addition to the reactor specific needs, there's also needs to understand defects in these materials. So even though they're single crystal, there's still a lot of defects. There are voids, there are grain boundaries, there are point defects like chalcogen vacancies. And also you can have regions that have multi-layers on them. So bilayers or multi-layers on a monolayer film. So there are needs there in order to develop techniques where we can characterize defects on wafer scale films, and of course correlate defects with device performance, and then ultimately eliminate the defects. There's also needs to develop methods for selective deposition, right? Selective growth, so we can deterministically place the TMD domain where we want it. There's also a need for doping to be able to control the carrier concentration in the layers, and specifically to do selective doping for contacts. And then finally, we need advances in terms of layer transfer. So, if we're going to use layer transfer as an approach for device fabrication, we need ways to transfer large area films without introducing impurities, and also things like wrinkles or other additional defects. So with that, I'm going to stop, and then I would be happy to take a question or turn this over to one of my other panelists.
Thank you, Joanne. Very nice, very interesting. A question. I'm wondering if you are interested or using artificial intelligence in some way for your analysis, your characterization of the materials, and how useful this kind of techniques could be in the future to, have a more global and systematic, determination of the materials. And also, is it possible to acquire data while you are growing the materials, maybe to also gain information about the dynamics of the growth that Kostya mentioned?
Yeah, I think that's where in situ monitoring comes in. We need some techniques to be able to tell us something about the growth process, but ideally if it could tell us about defects. So, the level of defects that are being introduced into the film during growth. And I think that's where there are going to be opportunities to integrate it with machine learning and to have some active feedback control of the process. Ultimately, the goal is to have an autonomous system for synthesis of 2D materials, but I think there are a lot of steps along the way that will take us there, but also just provide a lot of valuable information along the way.
Mm-hmm. Okay, very nice. Thank you, Joanne. We'll continue later. So let's move to our third panelist, Professor Yuri Gogotsi. So Yuri is a distinguished professor and director of the Drexel Nanomaterial Institute in Philadelphia. He's a world leader in the field of synthesis and surface modification of inorganic materials, such as nanodiamond, nanotubes, carbide-derived carbons, and also especially two-dimensional carbide and nitride, better known as mxene. So he's really one of the leader of the field. His group mainly explore energy-related application of these materials. So looking forward to hear you, Yuri. Thank you. Your microphone, Yuri, please.
Okay, I'm unmuted myself.
Yeah.
And
okay.
Can you see my presenter screen now?
We do.
Okay, excellent. So I'm going to continue the topic introducing another class of two-dimensional materials. Specifically, we call them mxenes, two-dimensional carbides and nitrides of transition metals, but not only, because following up on what Kostya mentioned, I think the future is really in assembling multifunctional materials from two-dimensional building blocks. This is how I believe we will be making materials and devices in the future. And as you have already heard from Kostya, there are many 2D materials available. You have heard about graphene, dichalcogenides. In 2011, with my colleagues and students at Drexel, we discovered 2D carbides and nitrides, mxenes, where M stands for a transition metal, X carbon and nitrogen, T means surface terminations. You can build them out of a dozen of transition metal. Lanthanides can substitute for one of them. Carbon, nitrogen connect metal atoms in these layers, and the surface can be oxygen, hydroxyl, amino groups, chalcogens, halogens, phosphorus, antimony. If you do just a simple mass of combination in 4 basic structures from 2 to 5 layers of transition metal, you already end up with about 1,000 possibilities. But we can make out of plane ordered structures, atomic sandwiches, where one element, for example, chromium or moly is on the surface, another, for example, titanium is in the middle, or structures with alternating atomic columns of different elements, or each one of them away and get atomic trenches on the surface. And of course, we can match and mix up to, for example, 7 elements in high entropy multi-element mxene. So I hope you get an idea. We can virtually end up with an infinite number of these two-dimensional building blocks of the future technology. What is important? Carbides and nitrides are very strong. Actually, they're stronger than other solution processable 2D materials here. And they have metallic conductivity. Without surface termination, all of them would be metals. Surface termination can open band gap in some of them, but again, they're metals, but they also have ionic conductivity between the layers because of these terminated groups here. And of course, a variety of properties. Naturally, you cannot experimentally make an infinite number of 2D materials here. We also use DFT prediction and machine learning. This is from some earlier work with Vivek Shenoy. Other groups also do similar prediction, how, for example, make out of max phases, so known mxenes, by removing a element. And this is work from Linköping recently, predicting not only carbides, but also two-dimensional silicides, synthesizing one of them to confirm here. So clearly, computational science, machine learning, artificial intelligence will lead us to the world when we have all the necessary building blocks to create this type of multifunctional materials by combining different structures. What we can do with this? When we specifically do it not by CVD, but by assembly from solutions, where we can produce a large amount of materials, like mxene can be produced in kilogram properties, even in laboratory. We can assemble them into flexible variable energy storage devices. We can shrink batteries, make transparent electronics. We can manage the heat, for example, preventing heat losses to environment by low IR emissive materials. We can also create soft robots by using electrochemical actuators and do many other things. This is an example from the work published recently in Science by Chun Fen and Ray Bachman, demonstrating that co-assembling graphene or graphene oxide initially with mxene layers, it's possible to create materials which are far beyond any like a single materials, even like a carbon fiber fabric composites, having strengths of about 2 gigapascal, like 5 to 10 times stronger than aluminum, at least twice as strong as steel, just by assembling them and cross-linking their organic molecules. And these materials can also serve as supercapacitors storing energy. So it's a really new opportunity study. We assemble them to make batteries, supercapacitors. We use very thin layers of mxene to make flexible light-emitting diodes, collaboration with Korean scientists, but also instead of ITO, when 2D materials are used, they become flexible, foldable, even stretchable. But moreover, by tuning the work function, we increase by almost an order of magnitude luminous brightness of those devices here. We can take a plastic component printed, for example, this waveguide for low Earth orbit satellite, deep into mxene solution, and it starts performing like a metal, being 10 times lighter and about probably 100 times cheaper, even at today's prices of 2D materials here. And we can make a 200 nanometer film, which will enable, when put on a hot plate, temperature drop of about 100 degrees C. Imagine every building coated, spray coated, just like you paint the surface of the building with a film that prevents heat losses and cuts our heat bills by 30–40%. And taking into account that about 15% of all energy in the world used to heat or air condition in the hot part of the world buildings, this is enormous here. So this is what we envision for the future for the assembled materials. When we assemble same or different 2D materials with eventually organic molecules, polymers, produce them in large quantities, control their mechanical properties, colors, plasmonic, optical properties here. We can make devices which are thin, materials which are strong, environmentally stable, but at the same time multifunctional, smart. For example, shape morphing wings that also serve as a storage device and a structural material at the same time. And I think there is a really bright future. We have learned how to make a variety of materials. We're learning how to assemble them and produce materials with properties that no bulk material has today. Thank you.
Very much, Yuri. Very nice presentation. So, yeah, I have a curiosity question about if one is interested. I mean, we are not involved into the mxene research, but we are interested to obtain a certain quantity of a particular mxene to make some tests and so on. What are the options? Are there any companies that are already selling materials, or do we have to connect with a group like yours? What are the possibilities?
You can, of course, connect with us, but there are multiple companies. There are a couple of dozens of companies in China selling materials, company in Ukraine, for example, Carbon Ukraine, Inomaxine in Korea. There is a company actually coming from Manchester Graphene Center that has a license to produce mxene from Drexel University. My students started recently a company, Mxene Inc., to manufacture inks of mxene. And of course, there are big corporations. For example, Murata is Japan in one of the leaders, and it licensed numerous patents for Drexel University here. But even Sigma Aldrich sells several mxenes today. So there are multiple commercial sources as well. And of course, there are 1,000 researchers around the world who also make their own materials.
That's important. push forward the field. Thank you, Yuri. So let's move to our next and last panelist, Professor Cecilia Matevi. So she's Professor of Material Science in Department of Materials at the Imperial College London. She's very well known in the field of science engineering of novel two-dimensional materials for application in energy conversion and storage. And our research activities are broad, from material synthesis to device integration and technology development. And she's also very experienced and involved in developing large-scale productions of graphene-based composite for practical applications. Okay, Cecilia, the floor is yours. Thank you.
Thank you very much for the introduction, the opportunity to talk today in this very interesting webinar. Yeah, so the title of my talk is from 2D and to 3D, and I'm going to focus on one of the aspects of our research, what has been interesting us in the last few years. Okay, so so we can see, as we know, that there is an increasing. Sorry, just have to understand how. Okay. The wearable and portable devices are becoming increasingly essential in our daily life for the acquisition of data, processing of data, and sharing of data and information. And the market of wearable devices has been increasing over more than 5 times in the last few years, or even 5 years. The further development of wearable devices is tied to the development of power sources, so portable power sources, as such in the form of rechargeable batteries. But now the demand of this and the characteristics of these rechargeable batteries has increased. So they should be lightweight, inherently safe, reversible, and very importantly, customizable in shape. So there is a manufacturing technique which can enable possibly such miniaturization and customization of the design of the battery to make them small, over small footprint area, and of different design that can suit the different types of wearable devices. And such techniques is 3D printing, in particular in the form of direct ink writing. So this is based on a layer-by-layer deposition of a viscoelastic ink, which is extruded through a nozzle. And the nozzle normally those nozzles can have very small diameters, like in the order of tens of micrometers up to a few hundred of micrometers. And what is key here is to have a very highly concentrated ink, which is still in a fluid form, but as we call it, a viscoelastic ink of a functional material. And 2D materials from transition metal dichalcogenides to graphene to mxenes present very interesting electrochemical properties for energy storage. And at the same time, as we know, they are confined, they are small, so they could be particularly suited to be used to formulate such ink. And what we are going to formulate with those inks, or what are we going to construct with those inks, are electrodes which can serve for energy storage devices, from supercapacitors to batteries, in particularly miniaturized batteries. So that means that they are developed over small footprint areas, like less than a centimeter. And what is one of the main advantages of this 3D printing is that we can design any geometries that we would need. So we can print structure with arbitrary complexities, as we say, and we can develop the third dimension, which is beneficial to increase the energy density of any electrode, from supercapacitors to batteries. So what is key is to identify the right chemistry of 2D materials to form and those viscoelastic ink. So this is an example, for instance, of our recent work on some viscoelastic inks based on graphene. So as we know, graphene cannot be easily dispersed in water, but finding the right additives, the right surface chemistry, which we can actually design an ink which can be extrudable through this nozzle. And we can see those structures from the micrometer size, so we can recognize all these plates of graphene and can form these regular struts in the order of 100 micrometer range. And looking at the microstructure of this, we can print different number of layers of different geometries and with different thicknesses. What do we use these structures? So we use as electrodes, can be used for micro batteries like this interdigitated to supercapacitors. And then those batteries can have adequate capacity and energy density and power density to also power sensors such as we are all familiar with Bluetooth proximity sensors. So the challenge is really to find the right palette of materials and chemistries and to try to screen those combination of surface chemistry and 2D materials via high throughput techniques to be able to identify suitable combination of materials as cathode and anodes of batteries, and also looking at different chemistries of batteries, not the traditional chemistry that we are familiar with like lithium-ion batteries, but looking at different chemistries. And the third component, which is very important in the battery, is also the electrolytes. So having an holistic view here and looking at the combination of 2D materials with, for instance, polymers or soft matter for their own dispersion in liquid phase, but also for the combination and for the integration with electrolytes would be highly beneficial for fast-pacing progression in the direction of miniaturized batteries for wearable technologies. And with this, I have concluded my presentation. Thank you.
Okay, thank you, Cecilia. Interesting. I have a question. Do you think that biomimetic design strategies are a way to boost the performances of energy storage device? And are you involved into this type of activity?
Yeah, well, certainly it's the next step of wearable technologies. So it's a further down, I would say, in the development, but certainly would be very interesting to see and to have an integration of batteries which at that stage would have really a different conformation and completely different structural design, and even also almost principle of operation in a fully biomimetic system with sensors. So the key is really to use these batteries for new sensor for continuous monitor, wireless monitoring.
Okay, great, thank you. Okay, so now we enter into the discussion and taking questions from the audience. So I will start. There is one question, so by Murat Eskin for Yuri. So the question is the following: is it possible to color mxene structure, not as in blending into a polymer and coloring via using a pigment, but coloring mxene itself?
Oh, well, first of all, depending on the composition, mxenes will have different colors, and those will be complementing plasmonic color in solution or polymer blend or on the surface. For example, titanium carbide mxene titanium 2C absorbs at about 550 nanometer, similar to gold nanoparticles, so it will be red in solution and green in reflection in a film, just like, for example, gold nanoparticle red in solutions. But you add another layer of titanium carbon, make titanium 3C2, and the absorption peak will shift to about 780 nanometers. And as a result, titanium 3C2 will be green in solution or in polymer blend, and will be kind of a violet metallic in reflection. At the same time, of course, when you have high concentration of particles in polymer or elsewhere, they may just look dark because they will be absorbing light at certain concentration, making material dark. Then you have to use a pigment to simply paint the surface of your component device. But mxenes come in many different colors, and it gives also rise to a number of optical plasmonic applications based on their colors.
Thank you, Yuri. So another question from Vincent Bouchard that maybe you know, some of you know. So he said, I have a question related to the industrial scale-up of 2D material for nanoelectronics. I am surprised to see that the upscaling is mostly discussed at the wafer level, which require costly batch processing typical of silicon technology. Indeed, 2D material being intrinsically flexible materials, roll-to-roll processing seems to be much better adapted. Besides, roll-to-roll unlock the coupling of 2D layers with printing technology and inkjet processing, which will dramatically reduce the production cost and scale-up speed without compromising the quality. What are the roadblocks against roll-to-roll production of 2D materials and their 2D integration? So I guess maybe we have some answer from Joanne, Cecilia, and maybe also Kostya. I don't know. Joanne, do you have some interesting roll-to-roll, and how do you see?
Yeah, I think roll-to-roll would definitely be the ultimate manufacturing process for 2D materials. It really just depends on what the application is. I think in terms of semiconductor integration, probably roll-to-roll is going to be a difficult thing. Just because if you're trying to get films that are largely single crystal, that could be very difficult to do if you're using a substrate that's compatible with roll-to-roll. But I think for other applications, particularly some of the applications that the other panelists mentioned, I think roll-to-roll could be the way to go.
Thank you. Cecilia, you want to comment also about the roll-to-roll?
Yeah. Well, in relation to the liquid phase processing and use of 2D materials, I would say possibly we would maybe envision that a specific production with already the chemistry that is needed for printing maybe would be viable rather than having the production on the 2D materials on their own. But possibly for a specific goal that would be produced along with the polymers and additive necessary to form these specific electrode structures.
Mm-hmm. You want to intervene? There is someone who directly asked you a question, Vedyapan Tirumal, I guess from India. So the question is, Professor Konstantin Novoselov, do you believe that graphene still holds promise as a material for technological advancements? Or what emerging development or alternative material do you foresee as next revolution beyond graphene? It's a very large.
It's you see, once we go to the application, because I presume we're talking about applications, because science-wise, it's really it depends on the kind of experiments you do. But if we talk about applications, it's not only the properties, it's also the cost, it's also the how easy is it to include into the production line, into the supply chain. So in that respect, I would say graphene is one of the most developed 2D materials at the moment, but at the same time, I can see that maybe other 2D crystals like semiconducting TMDC might outperform, actually, will probably definitely outperform graphene for semiconductor type of applications or light emitting diodes, so lasers. So I think we need to be here agnostic to the materials we use, and really think from the point of view of what this material can deliver, rather than just simply blindly put our bet on one or another. So it's a miracle that we've got so many of those. So we have a chance to choose the right material for the right application. So it would be stupid to bet on only one crystal.
Thank you, Konstantin. Another question for Johan. So question is, Dr. Redway spoke about the high temperature processing being not ideal for 2D material growth. Is this a problem for developing application other than 3D heterogeneous integrated chips?
Okay, so the question is, I guess what's the fundamental issue with high temperature growth? So yeah, the main problem there is if you're trying to deposit the 2D layer directly on a process device, right? That's where the temperature becomes a particularly limiting factor. So I would say the high temperature is specifically problematic for that type of application, but for other applications, it's probably not an issue. I think the questioner is correct that for other applications, high temperatures and layer transfer are probably going to be just fine. So yeah, it really, again, just depends on the application.
Okay.
I can probably add that even for graphene, I was to say the graphene is one of the most challenging materials. The temperature growth for TMDCs is much lower than for graphene. But even for the graphene, there are now novel methods of the growth which allow reasonable quality of graphene to be grown within the thermal budget of the CMOS technology. So I think we will. So it is an issue, but we keep finding novel ways of the production of those materials, and hopefully this can be resolved.
A question by Ilari Masenda. Owing to the low-dimensional nature related to high surface to volume ratio in monolayers, the 2D materials are hampered by additional source of disorder introduced by the substrate, roughness, impurity, adsorbate above or below the monolayer, commonly referred to dielectric disorder. What are the best approaches to this and understand what is happening at the interface in both 2D heterostructure and 2D 3D hybrid structure?
I think, Stefan, you are the best here to position to answer this, but indeed, so the disorder has been an issue for graphene science for many years, and I would say the most progress which has been achieved over the years is exactly because how we reduce the influence of disorder. So there were tricks being played, suspended devices, encapsulation in ultra clean boron nitride. The fact that Twistronix works so well is indeed because we use the graphite gates which screen the disorder on the nanometer scale. So that's indeed very much true. But at the same time, if you think about the scales which are available now in CMOS technology, we are at 5 nanometer at 5 nanometer nodes, but the thicknesses are even smaller. So having a metal gate, for example, in a very close proximity to either graphene or TMDC would provide an efficient screening for any of those impurities. So I would say both research-wise and the application-wise, yes, impurity interfaction is important, but we know the way how to avoid it.
Yeah, and also let me add something about disorder. Sometimes disorder can actually be good for an application. Not exactly, there are plenty of different applications, but sometimes it can be good. It has been shown, for instance, I mean, if you use two-dimensional materials which are like graphene oxide or disorder TMDs inside the stack of a peroxide solar cell, then you improve the coating of the interface provided by this disorder is such that the stability of the cells is improved quite substantially. Also, recently it has been shown that if you grow two-dimensional, or let's say thin films of amorphous boron nitride, you can have dielectric coefficients that are very low, and the material is more easy to integrate into interconnect technologies. So there are situations where the disorder can be actually useful for a certain device functionality. Also, I'm thinking about mem-restore. There is a lot of activity developing mem-restore based on disorder, boron nitride, or transition metal dichalcogenides. So there, the disorder is essential for the functionality of the device. So that will be really dependent on the type of application, and sometimes an imperfect materials can actually provide interesting properties for a given functionality. Okay. Yeah, I have a question. There are plenty of questions, but I have a question to Yuri, a question that I think it's interesting for everybody. So Yuri, you know that for 10 years, the European Commission has funded strongly the research in graphene. So although the research has diversified into other two-dimensional materials, I think that during this 10 years period, we have not been engaged into a mxene. But yet 10 years of huge funding, like 100 million a year, like hundreds of groups and company all together trying to push forward the use of this 2D material for application, it has been a effort. So I'm wondering, for the mxene, where you have shown that the numbers of possible combination is also quite wide, and or do you see the progress of these classes of materials compared to what has been done in graphene? Because I'm not sure that there is similar amount of public funding or industries involved and so on and so forth.
Oh, well, I think mxenes received probably about 0.1% of funding that went into graphene. But they have been developing very quickly. The number of publications is now achieving several thousand per year. There are papers coming from more than 100 of different countries. And last time I checked, like a half a year ago, maybe a year ago, in Web of Science, there were more than 60,000 people who co-authored papers on mxenes. Just in 2 weeks, there will be the Euro-mxene Congress in Spain, dedicated conference to mxene. There will be a conference at Drexel University, the third international conference on mxenes, in August 5 to 7, and the 5th international conference on mxene in China in October. There are also many symposia, including the one at the European Materials Society meeting this fall. So the activity is going on. But along the line of what I presented today and what Kostya just commented a few minutes ago, we have now a variety of 2D materials. No material is perfect and can do everything. The strength is exactly that we have semiconducting materials for devices. We have metallically conducting mxenes that can be assembled from pure water dispersion, colloidal water, no surfactant needed, no nothing, combined with other materials potentially, 3D printed, 2D printed. And at the moment, I think what we are identifying is where the important applications are. And we continue curiosity-driven research, discovering new mxenes, and I'm sure people will discover many more 2D materials. But we need also to be pragmatic approaching applications. We need to look for the best material. Which material can perform the work best? Or sometimes, again, as I showed today, it may be a combination of materials, graphene and mxene combined and linked by organic molecules produce a stronger film than pure graphene or pure mxene can make. And I think this is a way we need to go. We need to understand what materials are available and learn how to design with those materials future devices and do things that no other material can't. And in many cases, we have already demonstrated this with mxenes, but clearly mxenes now are a part of a large family of two-dimensional materials, and certainly with proper investments, they can solve a number of problems that other materials have not been able to tackle so far.
Thank you, Yuri. I have a question to Kostya. I mean, Kostya, the artificial intelligence, and you also put in your presentation, is becoming and is at the core of your innovation, design, and strategy. But what is the situation at the moment? Let's say, do you need to collaborate with external companies, or in order to get the state-of-the-art AI tools and also having access to platforms and computational resources? What is the situation in order for you to continue integrating AI into your developments?
Right. So first, thanks a lot for the question. I would say the most important reason for me why I see that the AI will be unavoidable to be used for the development of those topics, infrastructures, and the new materials is, first of all, that we are getting into higher and higher complexities and create more and more diverse infrastructures. So where computation, the traditional DFT approaches fail, so we need to guess a lot of parameters, and as of today, we don't have a solution how to bridge it. I really hope AI can help. Another reason is again what has been mentioned already. So is the linkage between the cross scaling models and the linkage between the growth conditions and the final properties, because the properties of those new materials, they're rarely dependent only on the chemical composition. So you have polycrystallinity, and you have defects, you have different phases, and that's all it needs to be taken into account. You either do it by hand, or hopefully AI can help. Now, whether we can do it on our own or not, so first you know about the foundational model, so you're supposed to create this neural network, give it all the information which exists now in the field, either experimental, theoretical, or from the literature, and it's supposed to give you an answer. In principle, you would say, after ChatGPT, all the other foundational models, the computer science part should have been developed. So we should just simply take that development and apply it to our field. Unfortunately, it doesn't work this way, because a lot of work is exactly in the fine tuning. You need to tell our neural network what to pay attention, what not to pay attention. And it's actually different for different materials. We figured out that if you're interested in the properties of the defects, for example, for single atom catalysis, the usual ways how to describe materials, they fail, because then if you have one defect among 1,000 atoms, and the AI simply misses this information, you need to bring it to the attention of AI. So
those foundational models, tuning of the foundational models is a really huge work, and that's where we need a lot of collaboration with the computer scientists. I don't think it will be a simple application of what already has been developed. It will have to be a joint development, and it's going to be quite a long process.
Thank you. There was some problem with the sound, but I think I mean we got right the answers, I think, quite well. Okay, so it's 2. So in principle, time is over. We still have some questions, but what we say is that we will make a file, and there's question on mxene, large-scale growth. But I think we have to respect the time, and so I would like to really thank you, our panelists, for taking the time to share with us your vision and your current activities, and also for the attendees that have joined this webinar. And I hope you enjoyed it, and do not hesitate to contact us individually. We will be always also happy to respond and to help. Okay, so I think I can conclude the webinar. Again, thank you very much for the time, and see you soon, Kostya, in Barcelona, and for the others, I hope to see you also soon. See you soon, Yuri, in Madrid, just a week before.
Great. Thank you
Bye
so
bye
much.
to everybody.
Pleasure.
Thanks a lot.
Bye,
Bye bye.
everyone. And also answer the few